All right, we're going to look at two special cases of circular motion that can be a little bit more challenging. The first is vertical circles. When something travels in a circle vertically, then one of the forces that we can't get rid of or ignore is the weight of the object. And so let's say, for instance, a good example of this might be a rock on a string being swung around vertically. I'm going to color this in a little bit. Okay, I'm going to look at it in two different places, at the top and the bottom. At the top, if I draw a free body diagram of this, I've got the tension pulling down from the string, and I've also got its weight. When it's at the bottom, the tension is up, but the weight's still down. Now, what makes this a little tricky compared to the other stuff is that I have more than one force that is along the line that connects the object to the center of the circle. Here's the center of the circle right here. When I look at the situation up top, both of those forces are pointing towards the center of the circle. And so when I substitute them in to this equation, I have to include them both. So I'm going to write this as mg plus the tension equals mv squared over r. If I were to solve this for tension, I get that it's equal to mv squared over r minus mg. All right, now at the bottom, I've got the tension pointing towards the center of the circle and the weight pointing away from that. So the expression I'm going to use when I substitute it in for this is that it is the tension minus the weight equals mv squared over r. If I solve that for the tension, I get that it is mv squared over r plus the weight. Now, what you can see is from these two results, the top tension is this expression mv squared over r minus the weight, and at the bottom the only difference is it's plus the weight, which means that the tension is greater at the bottom. As a matter of fact, if I swing it slowly enough, I can get a really interesting situation, which is when the tension goes away. Okay, so this is another add-on that we can do in a vertical circle. You will come across problems where they'll say things like, what's the minimum speed that you have to spin something around or rotating around, or if let's say it's a loop on a roller coaster, or any number of ways you can make something go in a vertical circle, what's the minimum speed to get all the way around? And if you were to take a rock and swing it from a string and go progressively slower and slower and slower, at some point you would actually feel the tension in the string go away when the thing is at the top. You would feel it just go slack. Or if this was a situation where you had a loop and you were, let's say you had one of those Hot Wheel tracks and you turned it into a loop and you made the car go around, you could get it going just slow enough where you'd actually hear it leave the track slightly. It would just not be pushing on the track. So what I'm going to do is let's look at what we see when an object is at the very top of its circular pathway and the tension goes away. Well, if that's the case, if the tension goes away, the only force we have is mg pointing down, which means that the centripetal force is just mg. And this gives me a unique solution where I have the relationship between the variables like this. If I were to solve this thing for the speed, I'd get the speed is just a square root of gr. If I'm going a little faster, then all of a sudden I'm going to start having tension again, and then I'm reverting back up to the equations I created up top. Another example of this would be if you were going in this vertical loop, let's say on a roller coaster, and the only difference is at the top, instead of having no tension, we have no normal force, because you can go in a vertical circle using the normal force, which would be actually going back to doing your laundry. That could be the dryer. And things go in circles in the dryer, and it's the normal force, again, pushing on the clothes that's making them go in the circle. But if it's a vertical circle, you'd have the normal force taking the place of the tension, the way we did it above. Now, another one that's kind of weird is when you've got a roadway that's curved like this. And let's say you have a little car and you're zipping along the highway and you're going over this curved roadway, and it's got a center of a circle down here, and there's a radius. And they want to know how fast would you have to drive that car so you just leave the ground. It's just catching air a little bit. And if that's the case and you're just leaving the ground, that means the normal force goes away. And once again, all you have is your weight down. In a sense, you're actually kind of in free fall. But the difference is you're moving in a circular path. And since you're moving in a circular path, you would have to use the centripetal acceleration form of the equation. But funny enough, the speed that you would go to just leave the ground in your car has the same expression for an answer as if the speed if you were going in a vertical loop and were just leaving the track. They're exactly the same. All right, let's move on to the idea of banked roadways. If I'm driving a car around a curve, I need friction to make me go around the curve. But there's a limit to how much friction you can get out of a roadway. And yet sometimes we'd like to have our cars go a little faster than they could by friction alone. And one solution to that is to bank the roadway. If I was looking at the roadway, it's tilted up a little bit. Probably should remind you a little bit of the problems we did back when we first discovered Newton's second law, where we had inclined planes. Now the difference is this is a car traveling along here. So I'm going to do my horrible car drawing. There it is. We're looking at it from the back. I don't know. I like it. You don't have to. Now, in this case, we still have weight straight down with the normal force pointed in this direction. Now, we are going to stick with problems that don't involve friction. Since the center of the circle is over here, so I'm looking from this kind of back view like we did on the previous video when we looked at cars going around curves or anything that goes around a curve using friction. This is the direction of the center of the circle, which is off here to the left here. Now, if you notice, I don't have any forces that look like they're pointing towards the center of the circle. However, I do have an angled force, which should have components. And this angle is going to be equal to this angle because of similar triangles, which means that this is going to be the normal force times the cosine of the angle. And this one down here is going to be the normal force times the sine of the angle because it's the opposite side from the angle. Now, if we look, what is pointing towards the center of the circle? The answer is that guy right there. So that must be our centripetal force. And so I can write that the centripetal force, which is equal to mv squared over r, I'm going to write in Fn sine of theta equals mv squared over r. And quite often in a problem like this, they're not going to tell you the normal force, and they're not going to give you the mass. And so it looks like we're done before we even started. However, we still have forces, one pointing down and one pointing up, which means that if I use Newton's second law, and since I'm accelerating towards the center of the circle, this has to be 0, I can say that the up force, Fn cosine of the angle, minus the down force equals 0, which means that the normal force times the cosine of the angle equals mg. Now, if I were being asked to solve for something that didn't involve the normal force or the mass, I could combine this equation and this equation by dividing the two. I'm going to take Fn sine theta equals mv squared over r and divide it by the other equation. So I'll have Fn cosine of theta and mg. And look at the beauty here. This cancels, the masses cancel, and sine over cosine becomes tangent. And we're left with the tangent of the angle equals v squared over rg. And you can have a lot of fun with that. Now this again, I don't want you to memorize this formula. I want you to be able to get this formula by making a free body diagram and creating it with the equations. But you can use this now to do any number of problems. You might be asked to, you might be given the speed and the radius, and asked to solve for the angle. You might be given the angle and the radius and asked to solve for the speed. And it really doesn't matter. You can manipulate this thing any way you need to.